This is the Aftermarket Radio Network. Welcome, everyone, to yet another episode of Diagnosing the Aftermarket A to Z. I'm Matt Fanslow, and your drug is effectively changing the world for the better. It's important that you know that. Crime is down, and oddly enough, so is tourism. That and more after a word from our sponsor, Napa Auto Tech Training. Check out our Napa Auto Tech Facebook page to find out the latest Napa Auto Tech virtual class scheduled at a time that is convenient for you. Learn from the comfort of your home. I kind of want to do something technical. I've done a couple of instructor-led classes, hands-on scope classes, and I just feel it's interesting to talk about motor current, electric motor current, be it starter or whatnot. And it usually begins with talking about starter current for a relative compression test, but it translates to more than just the starter motor itself. So in the description or whatever of this episode, there should be a couple of links to a Google Drive that's got some Pico files, PS data files. Those can be downloaded. And then if you don't already have Picoscope, this isn't like just some big ad for Picoscope, but it's free. The software is free. You can go download it, and it will let you open these up, not only just see them and follow along with this episode, but also manipulate the waveforms, which I don't intend on doing a ton of, but a little bit. It'll let you kind of follow along. If you don't want to download the files or anything like that, I'm going to try to discuss the waveform. And if you're somewhat familiar with like the relative compression test as viewed on a digital storage oscilloscope, or even really fuel pump current, any electric motor, I hopefully will do a good enough job here that you can kind of follow along with what I'm talking about. If you downloaded these files, I think there's two of them. One is going to be basically a bunch of numbers like 2024, 10/7. It's the date. It's a date. The next one will say something to the tune of relative compression bad. It's not so much good versus bad here, but there's different points to both the waveforms that bring up topic of discussion. And the reason I would like talking about this is I feel like we're maybe somewhat undersold how much information is in one waveform or one test with a couple of connections. So in this case, my examples, we're going to be using relative compression with a current probe, and the waveforms are of a starter motor. So they would be a high amp current probe, meaning, and I'm not speaking just for Pico, but in general, most high amp current probes out there for us to buy, regardless of manufacturer of the probe or the scope, range probably from, on the lower end, let's just say 500 amps, up to really 2,000. Now, granted, there's other ones that go a little bit lower, of course, or the ones that go higher, of course. But I think the main ones we see are really in that 600 to 1,000 range. More than enough, very effective for this test, specifically on starter motors or battery current, if you will. For other electric motors, low amp probes, typically anything under 100 amps, most of them 60 amps or lower, a lot of them 20 and 30 amps and lower, would be great for almost every other electric motor on the car. So we're going to make that connection. We're going to clamp on whatever cable's the easiest to get to going to the starter motor, in the heavy gauge cable. It doesn't matter which one. We just want to make sure we get the starter current. And I guess I got to be careful how I word that a little bit, in that if you're on the negative side of the battery, because it's available and it's easy to get to, and there's just the one big cable clamping around that, will get starter current. It becomes a little more of an issue if you have a couple of positive cables, if you will, red cables going throughout the vehicle. Maybe one goes to a power distribution center, the other one goes to the starter motor. We want to make sure we get around the one going to the starter motor, okay? Before I move on, more and more vehicles have kind of remotely located batteries. Then we need to get to the cable somewhere along the line where it goes to the starter motor. Or if we get right to the battery, we can clamp around positive if it's kind of a single cable, or negative, of course. Next, we would like to somehow disable the ability to start, preferably fuel. However that happens to happen. Okay, some vehicles have inertia switches we can disable or unplug, relays we can lift, fuses to pull that only really affect the fuel pump but would allow the engine to crank over. Some of them let us clear flood. We got to be a little careful on that. Not that it's a worthless test, it's absolutely a worthwhile test, but in some cases, when you clear flood some vehicles, not only do they disable fuel injector pulse, but they also disable ignition. And there's a little bit of data there that would be nice to have even before we make that connection directly to a coil or a plug wire or whatever, some way to find out when a coil is being fired or commanded to fire, something of that nature. So just be aware of that. It might be better off somehow disabling the fuel pump. Some cars are really easy to pop the rear seat cushion out, unplug the fuel pump directly. If we can somehow find a way to disable fuel, and I should say some cars are quite easy to disconnect injectors, especially on like 4 cylinders. You can have the 4 injectors unplugged about as fast as anything. And then we still need this thing to be able to crank over. Now that we've kind of got that all settled, I don't know that I need to, or how badly you would want me to cover like setting the scope up. I mean, honestly, we're going to go by what our current probe is. If it's a 500 amp probe, it really serves little purpose of using a scale that only displays 100 amps or would display 2000 amps. Set it up for what our probe is capable of capturing. And then time, we're going to crank it over for what? 10 seconds? 20 seconds tops? So you would want to get on a screen, whatever that time base would be, 20 seconds. So if you're going to have a scope that does time based by per division, time per division, and you have 10 divisions, 2 seconds per division, 1 second per division would be enough. If it's per screen and really snap-on jumps out, you want something where you're getting a second, 2 seconds, maybe even 5 seconds on the screen. We don't really have to worry about aliasing because this is a rather slow-moving signal. So it's not a big deal how perfect we get the scaling. With that, we can set our scope up to start capturing. Perfect world, we'd set a trigger on the rising edge of that current, or we're just sitting there ready to freeze our scope when it's done. Or when we start to see our scope starting to draw on the screen, we hit the key, crank. And then when we're done or we're getting close to the edge of our screen, the end of our screen, pause the scope. And you should have a waveform that sees a pretty good spike at the beginning that starts to drop off, relatively slowly, whatever that means, right? Starts to drop down in some triangular type of look to the rest of the waveform until we let off the key. That's what I want to start with. If you are using the waveforms that downloaded, namely that 2024 10.7, you're going to notice right at about, if you look at the very bottom of the screen, you're going to have time. So right on the 0, right where that yellow diamond is, that's the inrush current. That is not exactly accurate, but stall current. Meaning, if you think about an electric motor, especially a big one like the starter motor, if you were to take like an ohm meter to that, you would measure extremely low resistance. It's basically a dead short to ground. You could hook the starter up in series on the power side or the ground side of a few headlights, and they would power up just fine. They'd be nice and bright. Okay? It takes a fair bit of current to get this motor to spin, especially against resistance of the engine, turning the engine over. So with that, we get this big surge of current that we measure in amps. I would say normally we expect to see hundreds of volts, like probably on the minimum side, around that 500 amp range. I'm not saying if you have 480, you start worrying unless you are more familiar or fairly familiar with this engine specifically. And I'm not even talking about, 3.6 liters always do this. Really, the engine itself, like you've maybe scoped this before as a maintenance type service that you kind of know that you expect on this vehicle whatever surge, meaning a lot of cars are going to be in that 500 amp range and it'll be fine. Many you're going to see over 1,000 amps. It's fine. The key part is we want to see a lot of current and we want to be able to repeat that. So I know I said we might crank this engine over for 10 seconds or 20 seconds, but a really good test is to hit the key a few times. Like hit start, crank, 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 let off. Hit start again, crank, 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 let off. Starter buttons, a lot of times if you hit the start button, let off, and then let off the brake, a lot of times will disable the cranking. Or you can hit the brake a couple of times. That will stop it. The idea is I want to do this a few times in a row. If I get 10 seconds on the screen, 20 seconds might even be a little bit better. I want to do this over and over and over and over again. I want to see what that inrush current is after a bunch of times. Why? Because I want to stress that circuit out. I want to see that if it hits 600 amps, that it hits 600 over and over and over and over. Not once or twice, 10 times, maybe more, over and over. If I have a circuit that's flowing 600 amps, 700 amps, 1,000 amps, even 500 amps, over and over and over and over. Am I really worried about connections? Am I concerned about my battery terminals? Am I worried about connections at the starter? Am I worried about, is the starter grounded well against the engine block? Am I worried about a engine to chassis ground? Probably not. That's a lot of current flowing over and over again. It's a really, really good test. And it's not limited to just the starter motor. This works on every electric motor. Fuel pumps. If you're lazy like me, and there's a way to access the circuit, mainly feeding a fuel pump, and I can clamp around lift a relay and put in a jumper or a relay tester like the U-Activate or something of that nature, or I can get my current probe on the feed or the ground side of that fuel pump, and I can hit it over and over and over again. And honestly, I would like to be in a situation where I'm not disturbing that relay necessarily. If I can find a way to access that anywhere in the circuit, quite honestly, but with that relay in there, and I can hit the key or use my scan tool or somehow take control of the primary side or control side of the relay where I can hit that fuel pump a bunch of times in a row. Boom, 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 boom. Inrush current, inrush current, inrush current, 20 times in a row. And I see that it's hitting pretty high current. Like if the fuel pump is fused for 30 amps, I might be seeing 30 amps or a little bit more over and over and over and over again. Or if it's fused for 20 amps, I might see pretty darn close to 20 amps or even over. The thing is, it doesn't pop the fuse because it doesn't stay that high long enough to build up heat to pop the fuse. But you can see over and over and over if it hits that higher current for that circuit. Am I worried about connections at the fuel pump? Am I worried about a bad ground? Am I worried about relay contacts, especially if I've left the relay relatively undisturbed? What else is in that circuit? Maybe a leg of the ignition switch? I've proved it's all good very quickly without lifting the vehicle. I know. Done. Moving on. This works on every electric motor on the car, if we can control it to that degree and there isn't something disturbing, if you will, that current flow. And I don't mean like a failure type disturbing, like corrosion or a bad connection, but a controller. I'm thinking like window motors. Sometimes there's built-in modules that may affect the results. Just keep that in mind. Look at a wiring schematic. Is this just purely an electric motor as best you can tell? This stuff all applies. Napa Autotech training sessions are being conducted day and night in a town near you. This training caters to every level within your organization, be it a mechanical assistant, a mechanical specialist, a technology specialist, or a driver safety calibration specialist. Imagine a one-stop shop training partner in Napa Autotech that will lead your team to a path to greatness. Autotech's entry-level Build-A-Tech classes convert the untapped potential of your new hires into money-making mechanical specialists. Autotech's higher-level tech update classes introduce specialists to the world of ever-changing technologies, which prevents your shop from getting technologically stagnant. Remember, if you're not moving forward, you're falling behind. And, turning to the front of the store, the AutoTech Service Advisor class is an awesome way to hone your client advocate skill set, ultimately benefiting the customer through an improved vehicle repair experience. But it doesn't stop there. Imagine an electric vehicle class that takes your specialist well past the mundane, yet necessary safety topics. Well, it's here. AutoTech's EV Ready Training is a week-long curriculum that takes participants through a hands-on experience involving hybrids and electric vehicles. The session kicks off with the use of PPE and proper tooling while touching on required OSHA regulations. Then, the students dive into the lab vehicles to gain knowledge of the common high-voltage components on EV and hybrid vehicles and their function. Attendees will be taken on a path exposing them to different electric vehicle manufacturers to compare component form and location. Additionally, information about Level 1 and Level 2 charging systems will be included, along with a quick look at DC to DC charging. The operation and maintenance of subsystems are explored, including the different modes of Tesla operations, and so much more. So what are you waiting for? Commit to taking your business to the next level with Napa AutoTech training. Back to the waveform, we see that it's kind of starting to drop down in current levels. If you're looking at the waveform I linked that you downloaded, 2024 110.7, kind of drops down to where the peaks of those triangles, if you will, is kind of 200, a little bit less, and they have a very triangular look to them. If we start thinking about this as that starter motor's cranking, when does it work the hardest? If you answered as pistons are coming up on top dead center compression, you'd be right. So now look at that waveform. Look at those kind of triangular humps and think about pistons following that line, coming up on compression, building, going past TDC, dropping. Starter working, harder. It gets a break, up and down, representing all the cylinders in the engine. I don't mean all at the same time. It's one at a time, right? Following the firing order. The thing is that waveform I've given you no way to tell what cylinder is what. It's not that important right at this moment. What would you expect if we're comparing cylinders to one another? Even. We're looking for even peaks. It's a relative compression test. It's relative to the other cylinders. Older techs, and I don't know what that means anymore, are those familiar, maybe that's a better way. Those familiar with the older big box analyzers would recall having a similar test, and they may have called it the relative compression test. They may have called it, who knows, cranking compression test. I don't know. A lot of times they would do that test where they'd have a clamper on one of the battery cables, or they would just look straight at battery voltage. They would crank it over and they would get numbers. The highest number would be 100. 100 did not represent 100 psi of compression. It was 100%. And let's just say for grins that it measured 200 amps on the peaks of the good cylinders. The 200 would represent the 100. That was 100% of the current. Now, if you had a cylinder that was drawing 100 amps, it wouldn't show up as 100. It would show up as 50%. This is the same situation or the same kind of idea with what we're doing at it with this, only we're looking at it more visually. The peaks represent the current required to drive that piston up to TDC, and we're looking for those peaks to be relatively equal. I'm pretty darn close. Maybe not perfect, but we're not looking to really nitpick here. When stuff's bad, it's usually obviously bad. Like there's a big difference. We're looking for even peaks. While we're at it, not only are we looking at even peaks, we're also kind of looking for relatively even valleys. And more importantly, we're looking at the difference between the peak and the valleys. To kind of keep in mind, again, we're talking about relative compression. It's comparing itself, or we're comparing current from cylinder to cylinder. what if we have an issue on a car that's global, meaning it affects all cylinders the same way, and it affects it in such a way that it causes compression to drop? Maybe the timing belt or timing chain spun on the crank. Maybe, whatever scenario, I guess. It isn't all that important how. Just that, that's to figure out when it happens. But if all the cylinders are affected equally and the compression all drops, the peaks are all going to be the same. And again, if you are very familiar with the engine, you would know, this thing normally the peak should be 200 amps or close. That might be a tell. But if you're not, one way to try to decipher if you have a compression issue without intimate knowledge of the engine is to compare the peaks to the valleys. Then you would call that peak to peak. So on that waveform, if we're using Pico, if you go to the very top left of the scope screen, just above the amperage scale in blue, you'll see kind of a blue outline rectangle with a little triangle. If you left click on that and drag that down, that is a amplitude cursor, or in this case, an amperage cursor for channel A. And you can go up and grab another one, same place, drag it down, and you'll see a dialog in the middle of the screen labeled rulers. And I'll show you where ruler 1 is placed and where ruler 2 is placed. But in the third field, you see a little triangle, and that is a designation for delta or difference. If you're looking at the waveform I'm looking at, and you've dropped those cursors, it's right around 43, 44, maybe 45 amps, depending on where you've decided to set these. In general, we're looking for at least a peak-to-peak difference of 30 amps or more. Some people say 40. It's somewhere in there. Think about this again. If the hardest the starter works is when it's going up on compression, if it doesn't have to work as hard, we're not going to hit that peak. The starter motor is kind of spinning faster, so arguably less time to drop. That peak-to-peak shrinks, right? It's not as drastic. That's a clue. It's a clue that there is a global compression issue. Or, on a V engine, it would have to jump most likely at the crank or some fashion that way where it affects all the cylinders. On an inline, there's more options that would affect all the cylinders equally dropping compression, right? So got to be a little aware of what we're working on and what we're doing. But this is kind of a good way to point us in a direction. There's different scenarios that would drive you to look at that over others. One was there was an engine that the crank reluctor was really part of the flywheel. The flywheel, or flex plate, if you will, would break or crack, and the reluctor technically would, or not just technically, would really spin. It would rotate and then kind of seize again. In some cases, even almost re-welding itself into a position, but it was off. It would crank over in such a way that it seemed like it was low compression, and they wouldn't start, or they'd start and have lack of power, and you'd be sitting there because this is really pre-DTCs like we see nowadays. You had to make a decision of, is the issue on the back with the flex plate, or is it in the front with a timing belt or timing chain? This was a really quick way to decide, am I going to the front of the engine or am I going to the back of the engine? So just a quick scenario. So if you want to get rid of those cursors, you can just click the X in that dialog. It goes bye-bye. Just staying with this waveform just a little bit longer. Hopefully you haven't jumped ahead and messed around with filtering. You would notice, or hopefully you're noticing some voltage spikes or little noise spikes. And where they are occurring, they're occurring at or near those peaks just before. That's a reflection of ignition, or it is ignition. The spark plugs on this one are firing. Fuel was disabled. Spark plugs are firing. We're picking up some of that ignition noise in the starter current. And with that, I can tell rather quickly that I probably don't have an ignition timing problem. If I do, it's way off, right? It's off one cylinder away, depending on how many cylinders there are, would be how many degrees, right? But just a quick test, especially if this thing kind of runs, ignition timing's on. It's firing spark plugs at TDC. Like I said, unless it's way off, which does happen, you can tell my ignition timing's off. Think about what that would look like if that ignition noise was in those valleys and you're just doing this test as a, vehicle's got a lack of power or hard starting or something, whatever scenario you want, and you notice the noise. You've only made one connection. You've only hooked up your current probe, but you're looking at, my ignition timing could be off. What could affect ignition timing? All that with one connection. One. If you head over to the channel B, the field to the kind of the left towards the top, you have a red stopped button, if you will, at the top, and then channel A and then channel B. If you hit the plus sign in channel B, you'll have a waveform pop up, and hit that plus sign a few more times. Maybe the plus or minus 20 volt range is good or wherever. That is a sync probe. So this vehicle had plug wires, and I'm just had a sync probe around, probably cylinder number 1. And now I can see when those spark plugs are firing, and they are definitely at TDC. And on top of that, I now have visual proof for just somebody sitting here not working on the vehicle of how many cylinders are in the vehicle or on the engine, right? How many cylinders there are. Otherwise, there's really no way to tell, or it's difficult. I suppose you could work hard and find some signature humps that are characteristic to the cylinder, but the reality is that gets rough. Here you have visual proof of how many cylinders this engine is. And we can also see where they're firing. And then because I know which cylinder I have my sync probe connected to, if I'm a number 1 spark plug or number 1 spark plug wire, and it's a 4-cylinder, and I know the firing order is 1, 3, 4, 2, now I know which each individual hump, if you will, represents, which cylinders. That's how you find a cylinder that may be low to tell which cylinder is misfiring. Now, granted, most cars come in, they have misfire codes telling you which cylinder it is, but there's still quite a few. They don't necessarily code. Like, it's still the P0300. It hasn't identified the specific cylinder yet for whatever reason. Probably a different conversation. This hammers it home. If you bring it in, it's got a misfire, P0300. Depending on the car, maybe you can go to history misfires. I suppose mode 6, all that. But here's a quick way. 2 connections. Boom, boom. It wouldn't have to be a sync probe. It wouldn't have to have a plug wire. Do I have access to the coil? Can I get to the coil trigger, depending on how many wire coil this is? Something that gives me an idea of when that cylinder is firing. Can I just take my alligator clip and clip the clip the coil? I don't care to analyze the waveform. I just need to know when it's firing. Clip a penny and tape it to the top of the coil, or can I just lay my test lead near it? Is it enough to just kind of give me an indication that this coil fired? And then because of that, and I know the firing order, I can look up the firing order, I know which cylinder is which. So next, let's move to the next waveform. So you can go to the open button kind of in the top center of the screen, and you can open up that second waveform called relative compression bad. Hopefully you have that up. We have the pattern again, a different one. This one has some anomaly going on. Start from the left again. Stall current looks like it's going to exceed 600 amps. So again, do we have connection issues? And I'm not saying in this scenario we're worried about connection, but think about situations where you would be. This is a valid test. It's quick, down and dirty, and you can flag and pick up some really, really intermittent failures. You're really stressing that circuit out, right? Good thing to keep an eye on, not just starter motors, but electric motors in general. And now as that current drops, we're seeing peaks in that 240-ish range. But something's odd with this waveform, right? Couple of choices here. For fun, if you're following along, we could left click on the magnifying glass to the top right corner in the kind of the scope area, the scope screen or in the grid. Left click on that. That opens up a zoom window, and you'll notice that your cursor, your arrow turned into a plus sign. You can now left click and drag a box around whatever the area of interest is. So I have left click and drag just above kind of the middle of the waveform, like left to right. I've got like 3 of those repeating drops, and I've drew the box low enough to get below the red channel or the channel B below it. And I'll let go of my left mouse button. It now blows up. That box has basically become my screen. And I have a really, really good view of the starter humps, those triangular peaks. And I see I have a gap. Now, I've taken some of the mystery out of all this by setting my sync on the cylinder that was low compression, because that's what we're looking at, low compression. The starter didn't have to work at all. So we know whatever I'm synced on, that's the low cylinder. If I'm on cylinder 1, we know it's cylinder number 1. If I'm on cylinder number 4, we know the low compression's on cylinder number 4. If I wouldn't have picked the cylinder that's actually low compression, it doesn't matter which cylinder I'm on. And if that red sync is on one of the normal looking humps and lined up with the peaks, if I know what cylinder it is and I know the firing order, I can figure out which cylinder is low. So just looking at this, you can lift up that channel B by going and hovering on the voltage scale. So you'll notice as you bring your cursor over or bring your arrow over, or the plus sign technically, on top of those voltage scales, it changes, right? It's got a little arrow pointing up and an arrow pointing down. Now you can left click and drag up and down that 0 line, effectively moving the trace. And you could lift that up high enough to go, okay, I can see that this is firing at top dead center. Again, is it important for this specific concern? No, but you can see this over and over again, like this, I don't want to call it a phenomenon, but this aspect of the testing, you can see that. This is repeatable, that this is something to look for and keep in the back of your mind. The reason I put this on here was there's a little bit of a phenomenon if you're paying attention. We have these really fairly even peaks on 4 of them. Then we have the really low current for the cylinder with really low compression. And then we get this surge that's a fair bit higher than the quote unquote normal looking 4. So why is that? And I've been in some classes where it's, I think, brushed over, and it's not terribly important. Like the diagnostic value is not that big. But if you think about it, the way the engine works, it's kind of interesting to think about. I've heard it stated like the starter motor spinning faster, which I suppose technically it is, but that's not really why we have this higher current level. If you think about those good peaks, the good cylinders, why the current levels are where they're at, think about the 4-stroke cycle with multiple cylinders. Let's just say that the first normal looking cylinder is cylinder 1. Just for the sake of discussion, the first normal looking hump is cylinder 1, and we'll just make this really easy. Firing orders 1, 2, 3, 4, 5, 6. So 1's normal, 2's normal, 3's normal, 4's normal, 5 low or no compression, and 6 higher than normal amperage. Think about this a second. 1 comes up on its compression stroke. Starter's working hard. Crank, the connecting rod rounds top dead center and starts its way down. And then cylinder 2's coming up on its compression stroke. Well, if 1's just finished its compression stroke and 2's coming up on its compression stroke, what's still in cylinder number 1? Whatever amount of pressure we've built up, or it's decreasing, of course, but there's a certain level of push in there. There's an air spring that cylinder is pushing down. Cylinder 1 is pushing down, helping 2 up on its compression stroke. And the same with 2 pushing down as 3 comes up on its compression stroke. And the same with 3 pushing down as 4 comes up on its compression stroke. And then 4 is going to push to help 5, but 5 doesn't need much help. There's not much effort needed at all, as we can see. Very low. And then 6 comes around. 5 built up very little to no compression. Therefore, 6 is not getting the benefit of the air spring. There's nothing helping push it up. 5 is not pushing its piston down. 6 is getting no aid. The starter has having to work harder because it doesn't have the benefit of the air spring. And that's why we get this higher current level or peak. It's just interesting. I mean, is there a lot of diagnostic value in that? Probably not. But again, it's almost like in-cylinder waveforms. Looking at that 4-stroke cycle, looking at valve events and stuff like that, it helps deepen our knowledge and understanding of how things work. And maybe someday it comes, it kind of comes in handy. Think about active fuel management or displacement on demand, right? They're using the air spring function. That's a factor for the system to work. So that is how I will leave you. I hope that you find a lot of value in this. It's hard to gauge what everyone would like to see more of, because I get a lot of messages about wanting more technical stuff, and I also get messages about wanting more like theoretical and more like shop management type stuff, more personal stuff, and I like doing it all. So if this one resonates with you, or you'd like to see more stuff like this or other topics on the technical end of things, please fire off a message or send me an email at mattfanslowpodcast@gmail.com. And before we wrap this up, thank you to our sponsor, Napa Auto Tech Training. Thank you to the Aftermarket Radio Network. And as always, nothing happens without you guys and listening and, helping me out with different ideas. Just a quick update. Everything's good with Dad. I swear over the last few months, it's more and more like fully talking to the man he was before, or the person he was, if you will, before the event. Yeah, I guess it's just miraculous. It's the only word I got. The statistical probabilities of this is so astronomically low. It's like hitting the lottery. And sometimes I feel like I've hit the lottery quite a few times, and I don't play the lottery. Hit the lottery on quite a few different things. Parents, wife. Yeah, I've kind of covered that in a different episode, so I think it's about luck. So anyways, again, I really appreciate you guys listening, and until next time, take care.
You've been listening to Matt Fanslow, Diagnosing the Aftermarket A to Z on the Aftermarket Radio Network. Follow Matt on your favorite listening app. He's very interested in what you have to say. Let him know what you'd like him to cover and come on the show. Matt is all for advancing the aftermarket. Find Matt Fanslow on social media and connect or on aftermarketradionetwork.com.